Hey Ramblers, this video is going to cover chapter 3.7 in our textbook and deals with implicit differentiation. Now, implicit differentiation is not a shortcut like the rest of the chapter has shown us. It's really more of a technique, and we use this technique when we can't isolate y. That is, we can't get y on one side of the equal sign with everything else over on the other, just like we have with all the other derivatives we've been taking this year. We use this method, this implicit differentiation method, and we treat y as if it were a function that we could solve in terms of x, and we use the chain rule on it. So pay careful attention to how to the examples I show and how I do them, and take good notes. If you have any questions, we'll be going over it in class. Thanks for watching. We're going to start off this video taking a derivative right away. So here's something that's kind of familiar, or maybe it will be as the video goes on, you'll recognize what it is. But please take a minute and differentiate the square root of 9 minus x squared and see what you come up with. Okay, hopefully you saw that to find the derivative, we'd say y prime equals 1/2 the derivative of the inside, 9 minus x squared to the negative 1/2, times the derivative of the inside, which would be negative 2x. Now, I'm going to do a couple things here that I don't normally do. The first is I'm going to switch notations, and I'm going to call y prime by another one of its names, which is dy dx. And then let's simplify what we have over here on the right side. Well, clearly the 2 in the bottom and the 2 in the numerator are going to cancel out. So we're going to be left with an x over the square root of 9 minus x squared. Now let's just leave that there, and we'll come back to it a little bit later. Now, the purpose of this video is to talk about implicit differentiation. Now, implicit differentiation is used when we can't solve explicitly for y. For instance, y equals x squared plus x is an explicit function. We have y all by itself. But something like x squared plus 2xy plus y cubed cannot be solved for y. You simply, well, let's set it equal to something so you could solve. You can't get y by itself. So we have to use what's called implicit differentiation. And let me show you how that works. Let's look at an easier example, something that's not going to involve the product rule. Let's say we start off with x squared plus y squared equals 9. Now, in fact, you could probably isolate y in this case, but it's easier to start off with something that's not so difficult to function. So the idea here is that y is going to be treated as a differentiable function of x. Okay, as such, we have to apply the chain rule to it. So here's the example. Okay, if we're going to take the derivative of both sides of x squared plus y squared plus 9, we would get 2x plus 2y. Now, since y is a function of x, we have to apply the chain rule to it. So I'm going to multiply by the derivative of y, and here I'm going to call that dy dx. So that equals the derivative of 9, which of course is 0. Alright, so let's solve for dy dx. When we do that, we'll get 2y dy dx equals negative 2x. Dividing both sides by 2y leaves us with dy dx equals negative x. over y. Now that will be your answer. But if we were to bring you back to pre-calculus, you might recognize that this is just the derivative. I'm sorry, this is just not even a function. This is a relation that is a circle. It would be a circle whose center is at 0, that had a radius of 3, and it would look something like that. Now, in the previous slide, I showed you, or I asked you to consider and to differentiate y equals the square root of 9 minus x squared. Now that is this function solved, that is this relation solved for y. And when you did all the work, you got the answer that dy dx equaled negative x over the square root of 9 minus x squared. But do you recognize something? 9 minus x squared is equal to y. So I could rewrite negative x over 9 minus x squared as negative x over y. And that's exactly the same result I got when I used implicit differentiation. Now we don't have to go through all these steps every time. We don't have to solve it implicitly and explicitly, but I just wanted to show you that whether you use implicit differentiation or the methods we already know, you get the same answer. Okay, let's look at another couple of examples. Okay, let's go back to one of the examples from the first page, or the first slide. So this relation here, the directions are typically find dy dx. And finding dy dx is like performing any other operation. You have to apply it to every term on both sides. So to find dy dx, I'm just going to take the derivative of each term individually. Now pay careful attention, because in the middle we're going to need to use the product rule. And on this last term we'll need to use the chain rule. Once again, remembering that we're trying to treat y as a function of x. So in fact, we have a function of x inside the cubing function. All right, so let's go through this one step by step. All right, I'll start off with 2x, and then this next one, the next term, I'm going to need to use the product rule. So the derivative of the first is just 2 times the second, which is y, plus the first, which is 2x, times the derivative of the second, which is the derivative of y. That, of course, is dy dx. Then, the last term, since y is inside the cubing function, we'll use the chain rule, which would be 3y squared times the derivative of the inside function, which here is y. So once again, we'll multiply by dy dx. And that equals the derivative of 0, which of course is 0. Now, since we're trying to find dy dx, we have to solve for dy dx. So let's do that. Let's isolate dy dx on the left side. That gives us 2x dy dx plus 3y squared dy dx equals negative 2x minus 2y. Now, I'm going to factor out a dy dx on the left side, and I'm left with this final quotient, which equals the derivative. Now, in implicit differentiation, it's okay that I ended up with a y in there. That's going to happen. Okay, let's move on to take a look at another example. For this last example, why don't we do it in Zaption? So how about sine of xy equals 2x plus 5. And why don't you just find dy dx? just as we did in the last example. Okay, this again is going to involve the chain rule because x and y are a product inside of the sine function. So we're going to have the product rule going on inside the sine function. So we have chain rule too. Then the right side should be pretty straightforward. Okay, the derivative of sine is cosine, and of course we don't change the inside. But now we multiply by the derivative of xy, which is the product. So we take the derivative of the first, which is 1, times the second, which is y, plus the first, of course, which is just x, times the derivative of the second, which is dy dx. That is going to equal the derivative of the right side, which is just 2. Okay, now we have to solve for dy dx. To do that, I'm going to divide through by cosine of xy. And so I'll be left with y plus x dy dx equals 2 over the cosine of xy, which you could also write as 2 secant xy. Okay, I'm going to now subtract off y from both sides. And so I'm left with x dy dx equals 2 secant xy minus y. And so dy dx just equals 2 secant xy minus y divided by x. Okay, some of the answers are pretty ugly, but that's how you do implicit differentiation. Just treat y as a function of x and use the chain rule. Okay, Ramblers, thanks for watching.